model the behavior of complex systems, like airflow around vehicles, a seismic event, the climate, or combustion, on the complex system of the supercomputer.
By modeling airflow around vehicles, we can engineer efficient surfaces for minimizing drag and maximizing lift.
By modeling seismic responses, we can see into the Earth interior and find petroleum reservoirs or formations where we can sequester carbon dioxide.
By modeling the climate, we are better positioned billions of dollars worth of climate-dependent renewable energy equipment like wind turbines or solar collectors.
By modeling chemical reactions in flames, we can engineer cleaner gasoline engines and gas turbines.
At the Extreme Computing Research Center, we are engineers striving for efficient designs.
Scientists seeking nature's secrets.
Computational statisticians creating software tools.
And applied mathematicians like myself, seeking to describe the natural world to the virtual world. We accomplish this through simulation based on laws that scientists have derived from observing nature, or through emulation based on training a computer with large volumes of data. The computer is perhaps the most universal of scientific instruments. A DNA sequencer is for biologists, a spectrometer for chemists, an atom-smashing accelerator for physicists, a telescope for astronomers, and a sea vessel for oceanographers. But a powerful computer serves all comers. In our center, we strive to span the huge gap between the natural and virtual worlds through layers of software with carefully designed interfaces on either side of each layer for composability, so that scientists can efficiently express their questions. Computer engineers can provide responsive systems, and large, diverse teams can work together productively to ride the wave of increasing computational power. Through this computational power, we narrow down the range of expensive and time-consuming experiments that need to be done to verify their results. Computation and experiment are complementary to each other. However, experimentation might not always be feasible.
Some experiments we would like to perform with living organisms may be deemed unethical. Some, like the radiation aging of a colliding material, may take longer than the time we have to decide.
Other will-be experiments are impossible, like supernova, or prohibited by treaty, like thermonuclear explosions.
Other experiments are becoming too expensive, such as the ITER tokamak in France, to which about half of the world's taxpayers contribute, whose cost is now over $22 billion and growing.
Computation keeps its hands off nature, but provides a window through which we can observe the natural world in exquisite detail. Of course, we need experimental confirmation. Computations can narrow the expensive and time-consuming experiments that need to be performed. Today's computers can hold and access in parallel vast troves of data from natural observations, controlled laboratory experiments, and computational simulations.
Such data, interpreted through the right statistical models, can have enormous predictive power, independent of any time-honored physical models, such as the conservation of mass, momentum, or energy. The ultimate glory of the supercomputer is its ability to combine data and simulation.
Predictions from data alone, without good models, and predictions from models that lack good data are both prone to error. But data and models combined work together to improve accuracy.
We do so using our resources efficiently to get the answers with acceptable accuracy, with an acceptable expenditure of energy to power and cool down the computer itself. We do not want to change climate while trying to predict it.
In order to compute efficiently, in our center we exploit the property of many models called data sparsity. Datasets that come to us appearing to be very large, such as a set of correlations in between millions of data points in a climate model, can usually be captured with many fewer raw numbers if you change the basis in which you represent them.
Data sparsity, which reduces memory and processing requirements, entered the mathematical literature only recently and now has many forms. It powers lots of our work in the ECRC. We use it in our climate modeling in work that led to KAUST receiving a finalist nomination for the ACM Gordon Bell Prize. We use it in finding maps from structure to function in the genome. We use it in decoding signals in wireless communication. And we use it to remove the effect of atmospheric turbulence in earthbound telescope observations. But we're also enabling others to reduce the impact of their own computation. KAUST-authored software has been incorporated into commercial software libraries, including cuBLAS from NVIDIA, libsci from HP ECRC, the numeric library collection from NEC, and we're working directly with Intel, AMD, Fujitsu, and GraphCore to incorporate it into theirs as well. When I graduated as an engineer in 1978, computers delivered a then impressive 1 megaflops, or millions of floating point operations per second. 44 years later, we have computers that deliver 1 exaflops, which is 1 million times 1 million times 1 million operations per second. That's 1 trillion times faster, nearly 1,000-fold improvement each one of those 4 decades. How big is 1 trillion? Something that takes me 1 second to compute today would take about 32,000 years at the rate of computation when my career began. Any commodity which, on a regular and predictable basis, improves dramatically in performance while falling dramatically in price, attracts increasing usage. It seems that my students and co-workers will be part of a full employment program. When KAUST launched in June 2009, Shaheen 1 put the Middle East on the map in supercomputing. In June of 2015, Shaheen 2, about 25 times faster than Shaheen 1, catapulted KAUST back into the top 20 rankings worldwide. By June of 2023, we will place into service Shaheen 3, about 25 times faster than Shaheen 2. Our colleagues in climate, combustion, chemistry, and other fields will take advantage of a certain factor of performance improvement simply by compiling their code on Shaheen 3. But to take full advantage of Shaheen 3's capability, the Extreme Computing Research Center will be there with them, poking, probing, and exploring how to make their codes sing an even sweeter tune at the exascale, which is extreme enough for now.